And now we are coming back to Dr. Ali Inan. Ali Inan from EFR, Germany. His talk will be on accelerated smart meter deployment throughout Europe and the grid control impact in Germany. Dr. Inan, floor is yours. Maybe one word for the audience about yourself, who you are and where
okay. I'm from here, and I'm attending this meeting, this conference since 2004 every year. This is the first time in Jerusalem. Once it took place in Tel Aviv. This was 2009, I think, and hopefully next year in Eilat. Not because I love Jerusalem, but Elal was in a family atmosphere. You know, this is. But I'm, as you mentioned, I'm from EFR, but I have also a long Siemens tradition, I should say. And Avi Lugassi is also a good name, well-known name. We were in this smart, what is today called smart metering at the very early stage together. I will come back to this point later during my lecture here. But first of all, I would like to emphasize that we, as EFR, teamed up with National E to implement and providing end-to-end solutions for not only smart metering, but also smart grid, which is the main offering of our company, by the way. We have traditionally providing long wave broadcasting messaging services for energy management, load control, tariff switching, street lighting, and increasingly in the last 3 years also control of renewables in Germany. We have heard this morning, in the lunchtime, in the panel, also some information about what is happening in Germany. But why I called it accelerated smart meter deployment? Because since maybe 2 years there is a very visible movement towards deployment of smart meters, and where's the enter. No? Okay, it takes a time. So, but before I begin, so what is the reason we are doing this? There is, I think, everybody will agree upon the reason. What I would like to tell you, which is the resource awareness, whether it is economically feasible or not. We will come back later to this issue too. But this thing is very clear, and everybody will agree upon that. So the waste of energy was tolerable when electricity and other resource infrastructures were first built. So it was maybe back 50 years or 60 years. And today it is dramatically changed the situation, so it isn't tolerable anymore. So for the sake of the common generations, we have to cope with our resources very carefully and in an intelligent way. And exactly, it is time to actively manage our resources and eliminate this waste, drive down costs at the same time, because we would like to offer some benefit to all participants and cut carbon emissions and, of course, streamline operations. This is the global reason why we are doing this stuff. I would like to give you a short update about the smart metering in Europe, mainly because my focus point today is the European situation. So we have a push and pull movement. So the legislation is pushing massively, especially due to the European directive. All European countries have to go for smart metering, and the deadline was set to 2018. We will never reach this in all countries, but at least there is a target. This is on the one hand the legislation, which is massively pushing, and the market has started also to pull. And also we know today, especially what concerns the communication infrastructures, we have mature technologies available, more mature than it was 15 years ago. And all this accelerate the broad deployment of smart meters throughout Europe. When it comes to Germany, we have in Germany an evolutionary transformation of the energy generation. And this is going rapidly going decentralized. So putting upside down the generation level. So we have now generating, or the intention is in Germany at least, to inject power from the low voltage network towards the, if it is possible, of course, up to the medium voltage and even to the high voltage. And this, I call it power upload. So in the traditional sense, the traditional power generation can be compared with power download, so to say. So this structure is boosting. And also the smart meter penetration. Why I mentioned this aspect in Germany, it has to do with the justification, commercial justification of the smart meter deployment. When we come to the history, short history, how it began, I can say that it is, everybody will agree upon that also Europe was the cradle of the modern smart metering. Not so much the United States, because the United States was in an early stage, was going for so-called walk-by metering, drive-by, and even fly-by. So there were, due to the geographic extension of the country and different culture also, it was necessary to use these technologies or to collecting metering information. There is also a need for monthly billing, which is not true in Europe. And if you bill monthly, you have to at least read the meter 12 times a year, which is not true in Europe. In Israel, I think every 2 months, Avi. So this is one of the. So everything has started in the modern smart metering. What we are talking about today is started in Europe. And I can also tell you, based on our personal experience with Avi Lugassi, ICO was among the early frontrunners in the early 90s. And Hevrata Hashmal, yeah. In this time, when I was with Siemens, we have already had a solution, an end-to-end solution based on PLC communication, of course, low speed, but highly reliable at that time. It was an end-to-end solution. Even through the system, we could provide prepayment functionality. And it was deployed in the UK in many places, from Manweb, Scottish Power, and many others. And it was okay. It was running, but in terms of economical feasibility, it wasn't interesting at all at that time. When it comes to Italy, I can mention to you that Italy, before they deployed this large, I think 30 million meters, power line meters they have, Enel, they were always using power line, even in the early 90s. I know this because we had a factory in close to Naples, Casoria. Early 90s, they were producing and installing every year more than 100,000 PLC-based meters, PLC communication. Meters with integrated switch. By the way, the meter was a Ferraris type meter. And also in Austria, we did, you may remember, Avi, the same pilots, early 90s in Austria. And the system we have deployed was the first PLC-based end-to-end AMM system, which was called Mains Master. And at that time, we started a cooperation between Siemens and NISCO. Why I'm telling you that? Because these topics are coming back with slight changes. And even the first OFDM-based PLC trials, we have done it in the end 93. No, it wasn't 93. 97, 98, 99. So at that range. Before the bubble, the power line bubble came up. Yeah, exactly. This is today a top issue or top communication infrastructure which is about to be standardized. Now, it is also important to mention that at that time, mid of the 90s, we started from Siemens Landesendgear, which is now Landesplusgear, and Schlumberger, which is today Itron, to think about standard communication for metering. And it was DLMS with COSEM. And this has paved the way to today's standard, which is internationally accepted, except in Germany, by the way. Yuval has given a large information about what is behind the smart metering, but nevertheless, I will recap that again to make sure that we are talking about this functionality, which is the main, one of the main purposes was automated billing, which is clear. So collecting the billing information, the consumption data, and issue the bill. This is the main task for the billing. Next is the so-called interval data capturing and provision. This is for a 15 minutes interval, which is 15 traditionally or historically. It could be also 1 minute, every 1 minute. The solution we are providing today is you can choose freely the interval time. This is important now for example, for what we call dynamical tariffication, dynamical billing, based on this interval data outside the meter. It is today possible, not only possible, but also allowed by the authorities like PTB in Germany. If the data, which is transferred to the, let's say, meter data management system, is authenticated and also in a secure manner, which is today a prerequisite. Of course, remote disconnection and reconnection. This is a typical application which we know from the UK, where the prepayment functionality, also in South Africa, you mentioned this too, Ivan. So the meters has incorporate a switch. So I learned this during my that we call it customer management instead of customer cutting the customer. But if you tell customer we are managing the customer, it sounds more friendly. So another aspect is multi-utility metering. All these items are not true for any country, any company. But if you look at what is happening in Netherlands, for example, the utilities there, they have equal numbers of electricity meters or customers and gas customers. So gas is a very important aspect there. In Israel, not yet, but I know that this will change maybe in a couple of years. So therefore, the multi-utility metering is an aspect which is fundamental in Netherlands. Tariff management and demand-side management. Tariff management can be enhanced and coupled with demand-side management, which is controlling loads and equipment of the end consumers or end customers. Provided the communication ways are available. What we need to deploy smart metering, we need a communication infrastructure which has to be reliable and, of course, affordable. And another aspect which is important is to have standardized communication protocol. And last but not least, and this is also an item which is now coming up, customer privacy and asset security. Asset security is the most important topic, which also legitimates the use of the deployment of the smart metering in Germany, because we have alone in Bavaria more than 500,000 PV injection points. I call them hotspots. So they have, they need, we are talking not for privacy, but asset security. But privacy is a general requirement for any end user. Now, I am coming now to the main topic, which is prerequisite for any smart metering, smart grid, the infrastructures. I mean the communication infrastructure, and they are competing. So first, we have to look at the commercial mobile carrier networks, which is GPRS and IP-based communication, and also the pilot project is in Israel, in Binyamin, will be based on GPRS communication. This is good if it is available. If it is reliable enough, take it, and if it is affordable from financial point of view. But there are some issues with that. The one is the coverage is not, for example, if the meters are located in the cellar, like it is the case in Germany, so you have huge problems with the coverage. And the second is the mobile stations they don't have right now for commercial use a battery backup. So if the stations fail, so you have no communication. Another interesting point is some of the providers, they are changing randomly from GPRS mode to UMTS or 3G. So it might happen that you have no services for a while. You know why? Because they got more revenue from UMTS or 3G services than with GPRS. And another interesting point is that to reduce their power consumption, they are reducing the power so that the coverage can be affected. Next is what is coming up now in Europe, the dedicated carrier networks, which is CDMA based. I mean, it's not a step backwards. I would say rather a step forwards, because CDMA network is, due to the lower frequency, has a much broader penetration range, and it is considered to be built up separately, dedicated to the energy services. So this is getting more and more important. For example, the largest Dutch network operator, Alianda, has decided to deploy the whole meters through their own CDMA network. They will have in future 3 pillars. One is electricity, second is network, and second the gas pipelines or networks, and third will be the communication for them. So there is a comeback to the communication for the multi-utility. This is also true in Hungary, in Austria, and even in Germany. Large utilities in Germany are seriously interested in installing the CDMA technology because of the impact, governmental and legislation impact. The other option, I'm talking about infrastructures, competing infrastructures, which are believed to be important and prerequisite for mass deployment, not for pilots. So we are talking about mass deployment infrastructure. The third one, which is in discussion, is the advanced and standardized mains communication, which is G3 PLC. And this will operate in a frequency range from 150 to 500 kilohertz, which is much better than the Senelec band A. And EDF in France and also Spanish utilities are pushing this, and the followers are in Netherlands and even in Germany. So this is the number 2 solution for mass deployment. And the other alternative is the high-speed fiber optic networks in cities and municipalities. So those are, unfortunately, I'm telling unfortunately because this is the best solution we could imagine, only available in islands. But where it is available, go for that. This is my message. Now I'm coming to the very famous cost and benefit analysis to have an economical justification. So it is difficult to justify from pure financial perspective, at least if you only consider the metering, I mean only pure metering. So it is not clearly, very clear to say that it is legitimate. But it depends very much on the functionality, on the conditions of countries and regions. For example, in Italy, there is no question about that. As I mentioned, early 90s, they've deployed this. It is exactly tailored to the nations, their needs. Now, the interesting thing is what we have. We got recently the results of the study, cost-benefit study, which was awarded from the government to Ernst & Young, and they came up with the following results. So they identified that all customers for consuming more than 6,000 kilowatt hours per year, for them it is feasible to install so-called smart metering. I'm not talking about metering, but also the communication. And this is a typical German 22 million. What? No, it's about 10 to 12%. We have 40 million meters in total customers. It is about 5 to 6 million, not more. 2 minutes. Okay, I'm speeding up. So feasible for customers and injecting more than 250 watts. They will be forced to use the smart meter and smart communication link. Replacement with intelligent meters for the rest, and there is a separation between meters and gateway. So the gateway is a very important equipment which is providing all communications with this is TLS secured. The highest possible security is required there. Now, I will skip. This is what is behind this TLS authentication. This morning, Dani has mentioned this. This is very important. Asymmetric key exchange to establish a session for the data communication. Encrypted, symmetric encryption is part of that, and the extent of the encryption is not on the whole channel, and additionally, payload of the data traffic has to be encrypted additionally. Now, accelerated deployment. This is now to give you some information. In Germany, we are currently discussing about GPRS and CDMA with perspective towards CDMA. Also, 3G PLC in rural areas is of interest. Of course, fiber optics, as I told you, and injection is the very important item. In Netherlands, we have CDMA and concurrently G3 PLC, depending on the utilities there, but they have created a standard which is based on the LMS. And Austria will follow the Netherlands approach. Also, CDMA is that discussion then with the LMS and the same functionality almost. And this is also true for Hungary. I'm not going to go country by country. Those are some selective countries where the interesting decisions are taken or are going to be taken. In Poland, Prime, this is also PLC solution, is under deployment. And in France, will probably go after the first pilot with G3 PLC, and of course the LMS for the PLC solution. Now, this is maybe the solution I can give you. We are talking about the German-based solution. We have the meter on the one side. There's a pointer? No pointer. So we are talking about the meter. It has to be a TLS communication to the gateway, which is on the top of that. And this gateway is communicating through a TLS secured wide area channel to a protected zone. And then you can go to the application, whether it is data management, meter data management, or grid management. So we can share the same infrastructure, but we also can, and this is the way we will go for in Germany, for control, grid control. They are also, there's an interface to the so-called gateway, and this is also a TLS secured channel. So in total we have 3 TLS channels and one which is not displayed here, a wireless ambers, also encrypted wireless ambers for multi-utility metering. So go back to this, come to the conclusion, and this picture we can save for the discussion later. Some conclusions. Why high-speed communication? I'm convinced that we need a high-speed communication because we need an immediate demand response in the future. And we have to cope with dynamical network state in the future. We will have to deal with high granularity, density of end consumers and premises, hotspots. Real-time data is the result of that, and we have to handle this. And also balance the increased security overheads in the communication. So the linkage with the smart meters is to share this infrastructure, the same infrastructure, get the measurements from the meter, load profiling, I mean interval data, and dynamic tariffing and dynamic billing and balancing are the options we can get out of that. So I will stop here and thank you very much. Toda rabba. Dahem. And
any question to Ali? Yes. It is an invited question.
Yeah. Yeah. One utility, yeah. This is the one utility. The utility. This is the utility multi-metering, multi-utility. I can give you the company name is Alianda. They have as much gas meter as they have electricity meters.
Thank you, Ali.
No questions?
Thank you.
That's good. Thank you.
We've got another guest from Germany, Dr. Thomas Weber from Schneider Electric. And he'll talk about handling of low voltage systems with impact of regenerative power. Please, Thomas.
Okay, there's no pointer. Okay, ladies and gentlemen, I have managed in my first slide not to use the word smart, so I think the only one on this panel. And if I recognize the discussion I heard in the panel in the morning, I think Dr. Shlomo Wald had said he has a little bit of problem with the word smart. I would prefer intelligent, because smart for me has some kind of, let's say, a negative smell. But nevertheless, it's more or less a game to avoid such a word. It's familiar to everyone, so now also we use it. My presentation now will go, let's say, more on the power side, not on the data handling side, on the metering side, but on the power side, and facing some problems we have in our German low voltage grids, which may fit the problems which may occur in the future or already have occurred in the low voltage systems here. First of all, smart grid, try to describe, but okay, good. In Europe, in the European sense, we have an overall goal which is given us as a guiding line, which is the European power systems shall be in the position to be fit for the challenges and the possibilities of the 21st century, to fulfill the expectations of the community and to foster the open market. So for us technical guys, it's, let's say, a good sentence, but not so clear as we may like it. So we have to make it out of it what we need and what is possible on that. So one possibility may be that It's a very fine picture created around 10 years ago, and if you have a little bit deeper look on that, you find more or less every generation possibility as you like. And what is more or less the center of the game are the yellow boxes with the flashes inside. So that's beside the part what I'm facing with, let's say the power side. The side with these small flashes is the communication, the metering, and everything what you do with the data, which is of center importance. But let me say like that, without creating the power, dividing the power, transmission the power, every communication will not manage anything. So, in principle, a lot of slides are used to describe where we come from and where we go to. If we describe our old situation, it's a classical top-down structure, and if we look in the future and even in the existing days, we have a change of this top-down structure. Especially this can be seen if you manage the energy flow, which classically goes from top to down. And nowadays, even from low voltage systems, you can manage load flows coming above to the medium voltage side or from medium voltage to high voltage. So everything more or less has changed in our technical world now. And last but not least, this is the field of the other presentations where it's necessary to connect all participants of the system, including let's say the managing systems, the powering systems, also the economical parts and the market parts. So the main thing what I want to say is coming now in the next slides, which is the behavior of the low voltage systems as we know it in our field and measures to improve that. We have some rules, of course. First rule is from VDE, it's an application rule that if you have installation of photovoltaics, that you have a maximum allowed voltage step of 3%. This means the difference between all generation, low voltage generation, photovoltaic generation in operation combined with calculation without them shall be maximum of 3% difference. So additionally, in this new rule, they have learned a little bit out of the last years where no control schemes have been installed in the photovoltaic generation. And nowadays, this is the latest application rule, they have managed so that the photovoltaic in-feed shall be in the position to follow a power factor down to 0.9 instead the old solution where you have just a power factor of 1. Of course, you have general standards about the voltage band. So this means the nominal voltage plus minus 10%. And added in the lower part is that, of course, you have also some rules which are valid for the medium voltage part. And in the medium voltage part, you have also some influence down to the low voltage. So what happens in the low voltage system? If we come from the medium voltage here in red down to the low voltage and install in the low voltage system a photovoltaic plant here in a simple way, you have a voltage upload on the installation point, and if you are not really lucky, this may, if it's not only one or it's a bigger one, exceed the allowed volume of 10% as an absolute value, and additionally also the value of 3% in the voltage step. So, and with this problem we have a lot of intelligence to do and to handle such a problem. First of all, it's very simple. If we have transformers inside, we have also some tap changes, but as usually, I think in all our countries all over the world, we have tap changes which are between medium and low voltage as an offload tap changer. So this means if you have to change such a tap, you have to cut it off to go on by muscle power and to install it again and to repower it. So, but this you cannot change 2 or 3 times or 10 times a day. So this is normally done once and maybe once again if things have changed dramatically. So, and our transformers, for example, they have steps normally 2 times 2.5% in both directions. and according to the voltage level which you have in the medium voltage, you level the respective step so that you have in the low voltage system a reasonable voltage level. Another thing to be done is you also can change the equipment. This means in our systems there are some overhead lines even in the low voltage system left, and these are normally very poor lines. And if you reinstall and upgrade such overhead lines by reasonable cables, then you have electrically seen, let's say, a better connection of the infeeding point of the generation to the infeeding point of the transformer, medium to low voltage. But there is a time when the last overhead line has changed to cables, and what followed then is that you exchange the existing cable by a thicker one. And in our development in the last years, we could follow that over some years the utilities could not install cables as fast as they need to. So they install, for example, a 240 square millimeter cable. Half a year later, they have to install a 400 millimeter square cable. And again, 1 year later, it's not enough, and they have to reinstall a 630 square millimeter. And this could not be economically sensible. Yeah, and a new solution is, and now we are facing very slowly, but we will face the word smart, a solution where the technique which is well known from the high voltage to medium voltage is also installed in transformers from medium to low voltage. This means the installation of an on-load tap changer. So this means that you don't have to cut off the transformer to change, but you can use it as a normal transformer coming from high voltage side. What does this mean for the low voltage system? This means not a solution of every problem. So every time if you talk to our acquisition guys, they think this is a solution for the world. We as technical people always say, oh, stop, let's have a look before we use it for each and every project. Because the only thing what this transformer will do is to separate the system in the medium voltage from the system in the low voltage. So you can get by control an independency of the low voltage from the medium voltage side. That's what this transformer can do. And that's a lot, because if you do so, then you have really a big impact on the possibilities you are allowed to use in the low voltage system. I have brought with me a very small example, and you find a real power system investigated, and the numbers you see are the installed photovoltaic plants, very small ones, a little bit bigger ones, but it's a typical photovoltaic grid, a part of a low voltage grid in Germany. And all of these installed photovoltaic plants are installed using a power factor of 1. So they are producing 100% active power and no reactive power, in no lead, no lag. So, and what daily happens is that you have someone who is like to have installed additionally power, and we have on the top down left in the figure you find letter A. On this point, one customer likes to install additional photovoltaic of 30 kilowatt peak, and if you calculate that according to the rules, then you come to the solution that the available reserve in the power system is only 13 kilowatt, and this even using the new rules for this VDE application rule, so that the power factor is changed from 1 to 0.9. And of course, for such a system, this is not a solution where everyone or anyone can be happy, because this also will be followed by the fact that after that, this power system is full. So it's fully occupied by photovoltaic. And the next slide shows you what happens if we install such a transformer with on-load tap changer. And so what you see here in green is additional power, photovoltaic power, which can be installed by using such an on-load tap changer. Of course, we also have used here the installed power with a power factor of 0.9 to help the system. And so this means we have, by using this transformer, we have updated the capabilities of the power system to a maximum load. And of course, I'm honest, we have looked for a system where this effect is tremendously high. In a lot of systems which has to be checked, this effect is really not so high. So it has to be checked by system analysts and people like us, or like in my team, we are doing network planning. And before some realization of projects happens, so we are very happy to do some jobs. And that's what we are for. So, to make this a little bit more real, let's come to, first time to use the word smart. Also from an upper perspective, which parts and which positions are already in operation, which are near the market, which have a potential. And if you see the numbers from 1 to 7 or 1 to 8, you see especially that the higher numbers are seen for a time duration, let's say, between 2020 and 2030. For example, the hydrogen storage battery systems as matured systems, but we learned in the last days that the battery systems are not so bad as they are often seen. So they are, in my position, or from my feeling, they will be matured a little bit earlier than seen here in this figure. But on the right side, in the figures 1 and 2, here you have some communication structures which are available, and number 2, which is also available, is reactive power compensation, which may help systems very, very well. And we are dealing now in this presentation with number 3, which means the transformer with a tap changer between medium and low voltage. And here we have, meanwhile, a lot of pilot projects in Germany. A lot of companies are active in that. So the usual companies like Siemens, ABB, Schneider, Maschinenfabrik Rheinhausen. So everyone who normally deals with this power market. So this gives an overview what will happen in future. If you go to the band on the upper part, you see a gray line, which means the impact of simple load. So you have to imagine in that, for this course here, no regenerative is included. So this means if you have the old structure, a top-down structure, you feed in on the left side, you have some load, the voltage level goes down. And so before you come to the transformer, you have a certain reduction of the voltage. And then after the transformer is made so, or set so, with an offload tap changer, that the voltage level is reasonable on the downer side. And on the side in the low voltage, it goes up to the end customer, the last end customer on the right side, so that you have the lowest voltage level there. So this is, let's say, the old story, and if you see photovoltaic, the story at night, because if you have a high load and no photovoltaic and no storage, then this will happen also every night. So if you go back to the upper lines, the black ones, this means we have a system where we have installed wind in the medium voltage part and photovoltaic in the low voltage part. And this means that we have no problems with too low voltages, we have problems with high voltages. And if we regard here not our old transformer with an offload tap changer, but one with an onload tap changer, then you see instead of the word in the middle from constant changing to variable. So this means the voltage course in the low voltage system is much improved. Okay, so this is the theory. And this is a realization. So you see really classical layout of such a substation where you have several tasks to fill. The first was that our guys are asked by the utilities that they should not extend the existing sizes of the kiosk boxes. So if you create a new transformer, it has to fit also to the old places. And so you see here on the left side the medium voltage part, the transformer, and on the right side the structure of the low voltage side. This is the whole thing in reality. From left to right, you see the medium voltage part. On the right side, the low voltage, and the intermediate, you have a communication part, the protection part, and lower left, there is we say it's a quality cube, which delivers a lot of data, which, for example, Ali has then data to use and to organize and to manage. So that's the shape of this transformer. So it looks very classically, and I'm personally very sorry because this is our second generation of such a transformer. If you have the first generation, they had much more personality. It looks a little bit like R2-D2, if you know Star Wars. So here it's more or less a classical shape, where you have, in principle, a tap changer used in higher voltage situations, reduced in size and volume so that it fits to the shape of this transformer now. Besides the classical tap changing activities, we have also the capability to do this magnetically controlled, so that you have not expressively some steps, but it's going stepless top down and from bottom up. Good, and last but not least, to make the loop to the smart metering and control and data management groups which are necessary to make something out of the whole data which is created, which has to be managed. It's clear that it's absolutely necessary to follow standard interfaces and standard internationally used interfaces to make this interesting for big companies and not only for pilot phases. Let me come to a small outlook and summary. The importance of the low voltage systems nowadays, it's increasing. Up to now, the voltage systems, the low voltage systems are more or less, okay, here we have the customers, good, but we say the music is playing in the medium voltage and in the high voltage. But nowadays this changed. So in our systems, the PV generation is mainly installed in the low voltage part, and this based on some kilowatt per installation. As Ali had said, in the south of Germany are already 500,000 so-called hotspots where you have installation of very small photovoltaic generations. Of course, we have also big photovoltaic parks. One of the biggest is according about 60 or 70 megawatt peak, but of course not longer in the low voltage part. It's connected to the 110 kV. So what we have to do to be really smart is not only to use a transformer, but to optimize and to check the potential of such a transformer, if it's really necessary and sensible to use such a transformer, or to find some solution which can solve the problems elsewhere. And the smart kiosk, which I have shown, is surely a way where we can improve our communication skills. So even if we only use such a kiosk without this transformer and we use a classical one, even only using the new communication skills, then this would be an improvement. Then from the, let's say, power side point, if we do so in the low voltage and we use the existing volume to be installed PV power, then this has an impact on the medium voltage side. So what we have to do in our medium voltage calculations and medium voltage planning, we have to create a load or generation which is summarizing everything what comes out of the low voltage side. And this leads, of course, as an additional generator in the medium voltage to a voltage increase in the medium voltage level and has to be handled there. So, and what we need as future needs, so if anyone was there yesterday when I had the opportunity to have one of the keynote speakers, we have to define overall long-term strategy. And this means a strategy from technical point of view to have in our mind the goal where we like to go to. And we need very clear rules by the government, not only a rule where it said, okay, we like to have a 20% reduction and a 20% increase. No, they have to support the system utilities to have at the very end a cost optimization also for the end customers. We heard also in the morning about the cost that if you are a big buyer and you buy your electricity at an exchange, it may be, if you are a lucky one, you get the energy and you get money additionally. But if you're a small customer than me, then you have to pay for that additionally also. So insofar, it's not really a fine situation. Then the connection rules have to be adapted to the technical possibilities. If we have implementation of increased data management, of increased market and tariff policy possibilities, then we have to adapt the respective connection rules so that we can use everything in its best way. And the last sentence from my side, I can really recommend, because I follow up this now since 20 years, a strong collaboration of all partners. It's the heart of the game. And I can say in Germany, starting from the middle of the 90s up to now, I hope we have learned a lot, starting from, let's say, we have some green fools who install a little bit of wind, up to now where the green fools of last century are now partners, commercial partners, technical partners, which are fully accepted. So that's from my side, from this point, and I thank you for the audience. And if there are any questions, Gadi, it's yours. So some general remarks to the question about harmonics. I was in a research center in the 90s, and we started to implement programs and measurements for harmonics. And then in Germany, the market was installed, the global market and the open market. And to be honest, the harmonics, they were away. No more harmonics anywhere. But technically, I'm sure they are somewhere. So they are hiding behind the open market, and they will come back. And I'm sure if we go some years further on, we will come to the solution that these harmonics will come back and they will have some rules. And most interesting part actually is if you go in harmonics above the 50th harmonic, there is, let's say, galactical freedom. So you have every wideness to do anything. And what this has on an effect, nobody knows now and nobody cares now. But this will change sometime. So I think in our technical life we will see that we also have to manage that.
I would like to add something about the total harmonic distortion from PV. From some experience we have in Germany, we know that many meters that are stored to measure the PV energy were destroyed. Because of those total harmonic distortion. Because the meters were not developed to withstand the total harmonic distortion.
Okay, so that's not my perfect field on harmonics. That's clear. But I think if such destroyments are happening, some time will come that there is a reaction on that.
Yes, sure.
It has to.
Already, actually, this is ridiculous because we are talking about 5% voltage change, but we are blind. We don't see what is happening in the network.
Yeah, this is something what I say. All partners have to go to the desk to discuss something with one another. Not only the power part, also the communication part, and in some extent also the IEC standards have to be adapted. It's not a problem which we have in Germany. Maybe it's upgraded in Germany because of the local situation, but in general it's a worldwide situation because the voltage and the harmonic distortion is everywhere the same.
There's nothing, no definition. If you go
Yeah.
to PVD, they are only take care of the 50 Hertz main fundamental of the
Fundamental harmonic.
power, so which is completely compensated. There's no question about it.
Yeah. Thank you very much, Thomas. Thank you very much, Ali. We are going now to our final presentation. PhD student, Mr. Netzach Calamaro, and also an IEC employee. What? Ah, yeah, a gift. I forgot the gift. Oh. 5,000 shekels. Yuval. And for Netzach, a gift. Netzach, floor is yours. 20 minutes.
Okay. The subject of the lecture is a gathered list of all the effects that we know of the smart grid on metering systems, accuracy and correctness of measuring energy, and how do we cope with them. Now, there is a much detailed paper that we wrote for this convention, and if someone is willing to distribute the paper. It also shows that the distributed חשמל ואנשים. Okay, the objectives of the lecture are, as I said, to present a list of the smart grid effects on the energy measurement, accuracy and correctness, and show a methodology how to synchronize 4 complex entities. One is the standardization. Many people here dealing with metering systems know only a limited scope of the standards that we present here. The standards are there. The present technology effects of the smart grid on the metering problems with measuring energy, present the technological solutions, and start from the regulator rules. At the panel that was at the morning, we spoke about the regulator's rules. We see how to convert this rule to a scientific and engineering approach. We also show quite non-negligible effects. Provided we know about them, we can handle them correctly. On the physical measurement of energy from the smart grid and how we handle them. Okay. At the beginning, there is the regulator rules. The regulator rules haven't changed much at the 20 last years. To put it simply, the regulator wants the consumption report to be correct and accurate, all the energy consumption parameters. This is translated. 20 years ago, a digital meter, that's all there was. There were 4 energy parameters: active import energy, active export, reactive import, and reactive export. And all we had is that it displayed on the digital display, and the person comes every month and writes it down. Then came the consumption report and the load profile reports. Then comes the smart grid. So the data or the technology inflated exponentially. So beyond the meter, there is now both direct meter reading through a laptop or handheld unit, or a communication AMI software. So it's much more complicated now. And do we verify it all, that it works fine, that the consumption report is correct? There are a few doubts. In order to transform from the legal regulator rules, in Hebrew we say Amot Hamidah, they show at the internet, it's a book. We define a minimal set of engineering or scientific definitions. Why minimal? Because once they are minimal, everyone accepts them, and it's easy to transfer to an engineering and scientific plane. The first one is energy accuracy. The accuracy of the measured energy quantities. That was already 20 years ago when the first digital meters showed. We now add two terms, energy correctness, on top of the four energy measured quantities, active, reactive, import, export energy. There are 120 new energy parameters computed on top of them by multiplying tariffs, day-night saving times, holidays, and multipliers of load survey. All of these should be verified that the meter is working fine. So the first term that we insert to reflect the technology change over the 20 years is energy correctness. Okay? These 120 variables are standardized. The standard is DLMS COSEM. It's IEC 62056. It's a series of standards. So we don't invent them. It's an order of magnitude, meaning if someone puts import and export, it can multiplicate by 2 the number of variables. And the second term that we insert in order to have a coherent system on the energy metering nowadays is multi-layered verification. We shall show through this lecture that we can't satisfy with a single, like KEMA, verifying or certifying the meter with IEC 62056 or the Series 11 and the other ones. We must have a much wider set of standards. And actually at IEC we are enforcing them. Through these definitions, which are only three definitions, but they are engineering. Through the standards that already exist, we go to the meter testing. That's the way we go from the regulator's rule, simple rule, I want the consumption report correct, to verify that the meter is working fine for all the communication and AMI systems. In order to show the exponential growth that is affecting our verification, we show that there is an enlargement of the metering space dimensions in plenty very easy to understand dimensions. The first is the energy variable space. 20 years ago, and the standards reflect this, what we receive from KEMA certificate, 4 variables that we see on the liquid crystal display. Today, 120 official standardized energy variables that show at a standardized consumption reports, load survey reports, and we need to do something with them. We can't satisfy with these 4 variables at the liquid crystal display. This is an IEC, Israel Electric Company, consumption report. We see here the groups in order to see from where these 102 pull up. So what we see is from the left, the basic measured quantities, the active, reactive, import, and export. But then we see there is a max demand And it's very clearly one-to-one defined at the DLMS COSEM standard, and the cumulative max demand, and there are tariffs. The red one is the high, the yellow is the medium, and the green is the low. And then there are the self-reads, snapshots of the consumption once every month, 4 months backwards. And there is the load survey, the trend every 15 minutes for that period. The dimension of modules, software and hardware, has inflated. At first there was the meter itself, then a communication software at a handheld unit or a PC. Nowadays there is a remote system. All of them are processing the data. How can we verify that it's correct? We see nowadays that there are 2 consumption reports accepted by all communities. The first is a consumption report with the energy total variables, and below is the trend, what is called the load profile or the load survey. Another dimension that has inflated is the time axis. At the energy standards that we know, they are instantaneous variables. Now we need to have them accurate for 4 months backwards, and also in 15 minutes periods. And we don't check that. The standards don't, the standards that we know don't verify that. So actually there is a complete standard system, 22 years old, the DLMS COSEM. Most people know it, IEC 62056. Most people know it that it's a communication protocol covering all protocols, but it's actually free-folded. It's a one-to-one definition of the design specification of a regulated digital tariff meter. And the other issue is the verification. Once there is a one-to-one definition that applies to all meters in the world that are certified according to that standard, then the functionality is clear. Then we can extract the testing. So there is a news in here. For the first time, there's now a standard from the DLMS COSEM for testing. So we don't have to invent the tests from the functionality. Actually, there is a standard. So you see that all this work was hidden, okay? But it's actually the majority, 120 versus 4. Yeah. Regarding smart grid phenomena, these are phenomena that we measured. We thought that we invented the wheel, but then we saw that PTB, Germany, has found the same findings, the same meters. We don't say the meters' names. And also in Brazil and Spain. What we see here, that the converters insert for renewable energy technology, such as PV, inserts its nonlinear load. It inserts harmonics into the grid. It does it like a bad boy, not when we observe it at morning, but when we're not looking at it. But the power quality monitor is looking all of the time, so it records them. So about 1/6 of the meters at several kinds of photovoltaic technologies. It doesn't matter. There's not single naughty boy. There is a spurious or stray photovoltaic converter that behaves wrong. So we catch it with a power quality monitor. And what it does to the current technology of meters, it inserts inaccuracies. Now, when we're speaking about inaccuracies, we need to be careful, because every meter or every formula is correct up to a certain degree. So they are approximate, okay? The active energy, what is happening to the active energy? We show here an actual phenomena that occurs. The stray photovoltaic inserts distortion power, meaning harmonics at the current that don't exist at the voltage, and there is an active energy which measures accidentally also the distortion power. We see here the cube of the powers with up to 4% distortion. But we are talking about a population of about 0.1% of the consumers, meaning Okay, I'll be faster. At the reactive, it's even worse. Nobody measures reactive energy. Nobody verifies it's correct.
So there is no definition?
Yeah. But it's not so bad. For class 1 and 2 meters, the formula is approximate. It's a time domain formula. We see it above the book cover. Okay? For 99.9%, that's the actual percentage. It's okay. It's 100% correct. For the photovoltaic renewable energy, we need a class 0.2s or something, or 0.5 meter, which is more expensive, implements a Fourier transforms, and sees the harmonics. Okay. Okay, the conclusions are there is a large part of standards handling these subjects which we need to implement. For the physical inaccuracies, we need to implement at Europe the DIN 4110, which specifies all the legal formulas for meters. And at the United States, the IEEE 1459. The standards are nearly identical. There are very absolute formulas for it. For the subject of correctness of all these 120 variables that we don't check, we don't receive a certificate from KEMA checking them, the DLMS COSM, IEC 62056 specifies them and their testing. New meter technologies. For renewable energy, it is recommended, there is no rule about it, to use more precision meters, not because they are more precise, because they are more expensive. There is a Fourier transform inside them, and the formula is more accurate. It is absolutely accurate. I want to acknowledge two people enabling this research and also the access to data and receiving of data. One is Mr. Itzik Mashiach, the manager of the Metering Development Lab, who enabled me to use anonymous data for this report. And the other is Mr. Emil Kaufman, who enabled also access to this data. That's it.
Thank you very much.
Only one mistake. That you didn't put the right meter photo
For where?
in your lecture.
Intention. Okay.
I'm impressed from this department that they've got in this department one Netzach and one Mashiach. So with Netzach and Mashiach, it's the...
No,
Yes.
no, we don't need this.
נכון. with Netzach לא צריך. One question, one last question. Only one.
There's no other candidate. I will ask the mic.
Yes.
So let's up. You mentioned, which is true, 120
Variables.
variables.
Yes.
But to my perception, you don't need to check or validate all of them. So what is necessary is Itzhak should tell you or tell us what is beneficial for the operation of the network.
Actually, Yitzhak forces us, instructs us to check them all to see that they are coherent, but they are related into, divided into groups. So if, for example, self-read 1, all the addresses of these variables are a base address of self-read 1 plus relative addresses, which are like the current reading or self-read 2, okay? So if there is a bug, you find it in the group. So if you divide them into group, you remember the colors in the consumption report, it's much less.
Okay. Thank you very much. By this, thank you.